recorded from perpetuity. Cool, so we're in recording mode now. So go to Hooke's law. And we want to go to energy. Oopsie, I'm on the iPad, sorry, I'm an idiot, I'm on the wrong side. There we go. Okay, so you've got a spring, and the spring is at the currently in its resting position. So if I put the equilibrium position, you can see that, oh, I'm still clicking on the screen. I'm on the iPad. There we go. You can see the green line is at the equilibrium position. So what you can do is you can slide the spring, either extend it, meaning make it longer, or you can compress it, and you can slide it in both directions. And then what you can also do is you can plot the force versus displacement. So you can see there that I'm displacing it, and there's a certain value. When there's a displacement, there's also a thing. And then what you can do is you can calculate the area, because you know that the area under the graph is the energy. So you can see that there. And then what you have in the bottom left-hand corner here, what you have in the bottom left-hand corner is the spring constant. So you can see what happens when I increase the spring constant. I increase the stiffness of the spring, and therefore I can store more energy inside the spring. Also, for the same amount of displacement, I get more energy out, or in storing the energy. Cool, everyone happy with that?
Yes, sir.
Good, good, good. Okay, so I'm going to take it to a position. Now, unfortunately, this app, I can't screen share it immediately. So what I have to do is I have to take a screenshot, and then I have to annotate the screenshot. So let's see if I can do that. There we go. And then we go here, and then we use the pen. Okay, so can we calculate the energy of the spring based on the area under the graph, given the spring constant and the displacement? Who can remember the formula that we need to use from yesterday?
Kxf squared.
Correct. So I'm going to try and write as neatly as possible here, but we're basically saying that the potential energy is equal to a half ax squared, where everything obviously has to be in SI units. Cool, so we can substitute in a half. Read in the bottom left-hand corner, tell me what's the spring constant?
400 N-.
Correct, so newtons per meter. So 400 newtons per meter of extension or contraction. That's K. And then the displacement, I tried to round it off to 0.5, but I couldn't. But it's the bottom right-hand corner, it's the 0.505. So it's 0.505, and you square that, and then you can calculate the value. If you plug it into your calculator, you say 0.5, whoopsie, that's the previous 0.5 times 400 times 0.5 times 0.5, which is approximately 50. And because it's energy, we have to write it in joules. In other words, that spring, when it is extended by half a meter, is storing 50 joules of potential energy. Cool, everyone happy with that?
Yes, sir.
Pretty good, so we can go done and then save to photos. That's fine. Okay, so let's try a second calculation. Let's set it to approximately 240 newtons, and let's compress it instead of extending it. So compress it to approximately 0.7, give or take. Ooh, and then we've got to take a screenshot.
Can't you make it accurate by clicking on the arrows or typing the 0.7 in?
Can I do what? Sorry, say that again.
I'm saying, can't you make it accurate by typing the number in or by tapping?
I probably can. Yes, I probably can. Sorry, you're absolutely correct. I can definitely do that. Okay, so yeah, no, you're absolutely correct. I can definitely do that. So I'll do that for the next one. So again, we can calculate potential energy, a half kx squared. Spring constant is now 240, and the displacement is approximately 0.7, and we have to square that. And then you get the idea, you can do the calculation. So that's done. So save to photos. So let's see if what Tangi says is correct. I can't type in over there. I'm trying to click on it. I can't. But what I can do is I can move it incrementally with this little slider. So I can do that, and I can, yeah, there we go. That I can do. I can click on the little tab. There we go, to get it to exactly 0.7. Ooh, so the force applied. So what we want to do now is we want to think of a situation where the position of the spring changes and we want to calculate the difference in kinetic energy. So I'm going to make this as big as possible so that you can see it. So we'll start over here like that with a massive graph. Take a picture. And then what we're going to do is what we're going to say is we're going to move the spring to approximately half the displacement. So if this is 1, then this is 0.5. So I can't show you in the diagram. I can't slide the spring. But what I'm saying is I'm going to change the extension from 1 to 0.5. And then the question could ask, what is the change in potential energy? So what calculation would you have to do there?
The greedy, no.
A big EP minus a small EP.
100%. So you would have to calculate the EP here at that point, and you would have to calculate the EP here at that point. So you call that one big. Ooh, and then this is the small. And then you would basically say that you have EP big minus EP small. Cool. But would you also agree with me that it's actually just this area over here?
Yeah.
Yeah.
So in other words, it's actually the big triangle minus the little triangle.
Is it not?
So it's the area under the big triangle minus the area under the, that's an ugly triangle. Can I undo that? How do I undo that? Undo. There we go. Make it minus small. Oh, that's even worse. Doesn't matter. You get the point. But yeah, and then if you were not I don't know what the word is, but if you're aware of the shape of it, could you use a formula directly?
Trapezium area.
Correct area of a what?
Trapezium.
And a
Trapezium,
triangle.
correct. Yes, the area of the triangle would be the two-step process, meaning you calculate the bigger one and then you subtract the smaller one. But the direct method would be the area of the trapezium. So it would be one
Sir,
calculation. Yellow.
Is it like when you do this, does the spring constant have to remain the same all the
100%.
time?
It's exactly the same spring. So we haven't changed the spring. All we've done is we've changed the position of the spring. So in other words, if I extend it by 1 meter, it stores a certain amount of energy. But if I reduce that extension to half of that, I reduce the amount of energy stored in the spring.
Okay,
So
thank you.
each spring has a different spring constant.
Exactly, correct. So you get a tight spring and you get a loose spring. So the example that you guys did in class yesterday, you only used one spring, you only plotted one graph, and therefore all your calculations are based on that graph that you plotted. Cool, everyone happy with that? Yep.
Yes.
And then you can actually calculate energy values there. So it gives you that, there's the, I can't annotate on here, but if you want to, you can see from the graph, there's the force, there's the displacement, and there's that thing. Remember that if you don't have the spring constant, what is the formula you use if you don't have the spring constant?
Half fx.
Correct.
No.
It's yes, you are correct. It's a half f x.
X.
And in that case, I'm not using the spring constant. I'm using the force applied, and I'm using the f, which is 400, and x, which is 1. So a half of 400 is 200, and that's in joules. And I'll get the same answer if I use a half kx squared, which gives me a half of k, which is 400, times 1 squared, which is again 200 joules. So you have two methods. EK, EP, sorry, potential energy. potential energy. Everyone happy with that?
Yeah.
Yes.
Yeah. So I would call this a flyby chapter. When I say flyby chapter, it's like the chemistry guys will know what I'm talking about. It's like the rates of the reactions questions. These are not going to be rocket science questions. These are going to be like literally, here's a graph, here's a spring. Use whatever information you have available to calculate some sort of energy value or whatever.
So I have a question.
Yeah.
Will it always be EP? Could it be like EK2? Like let's say they asked us like the energy, like the kinetic energy that
Yes.
is moved.
100%,
Ooh.
because now you could think of a situation where the spring is used to do useful work, and whatever energy you can store in the spring, you can get out of the spring. So when you think about a spring and you compress it, let me go to a different app. There's another app that shows this quite nicely. If you go to this one over here, there we go, Energy Lab. We put a spring on. And you can see that I'm converting kinetic energy to gravitational, to elastic, to thermal. If we take away damping and we do that. But yes, the spring can convert potential energy into kinetic energy.
Mm.
So that is absolutely 100%. And then you can think of considerations like, is it frictionless or is there friction involved? Or is 100% of the energy stored by the spring converted to kinetic energy? So in this case here, it's being converted to potential and kinetic. But if you had the spring in a horizontal position, then the spring would only convert to kinetic energy. Not that one, not that one. I think the other one does it horizontally, so you can actually see it in a horizontal position. Not that one, not that one, not that one. Oh no, they're all horizontal. Yeah, there's no vertical, sorry, there's no horizontal one. But yes, you can convert all the potential energy in the spring to kinetic energy and gravitational potential energy. In other words, if you think about it, you could use a spring to lift something if it had enough energy to contract itself.
Yeah.
So if you think like if a spring had the ability to be stretched, have a load put on, and then return to its original position, it can,
Like a car spring.
yeah, like a suspension, correct, exactly. So the suspension, yeah, talk to me, say you speak.
No, it's what I'm saying, like the suspension.
Yes,
As soon as
100%.
someone heavy sits in the car, it goes down, but as soon as the person is out, it goes back to its original position.
Exactly correct. So the energy in your suspension is being converted into elastic potential energy. And then when you go over the speed bumps, it gets converted into kinetic energy because you notice the car wobbles a bit. So like these Formula One guys and these super racing people, they like what's called a stiff suspension because then none of that energy is wasted as kinetic energy. You basically go over the speed bump and you feel it. You feel like the gadump. You feel the bump immediately.
Or maybe bed springs, but some bed springs are not so lucky.
Correct. Yeah. So car suspension is a beautiful topic. If you want to add supplementary notes to this, you can actually go online and Google how suspension works. But that's it. So guys, I haven't got questions for this yet, so I'm busy still getting through that. So what I want you to do is I want you to keep working on your momentum questions because that's not a flyby topic. Momentum is a big topic and it's going to be worth, I don't know, it's probably going to appear at least once or twice in paper 1 and at least a 5 or 10 mark question in paper 2. So I want you to keep working on your momentum questions and then ask for help when you need it.
Okay, so
Cool. And then add this force constant stuff, quickly add it to your notes. And then once you're done adding that to your notes, go back to the momentum and carry on working with that.
Okay, sir.
Cool. There's a thing called Young's modulus. That's not a flyby topic. That needs a little bit of explanation. So that we'll spend a bit of extra time on, but we'll do that next week.
Okay.
Cool. So summarize your elastic potential energy and carry on working on your momentum questions. And then Gloria has a question for me.
Yeah, so on the on the graph that you showed us, you that dot, right? It even went on the negative side on the x-axis. How can the
Yes.
extension go less than 0?
Very good question. So if you look at the equilibrium position, we're saying that this spring, in particular, this spring can be compressed and it can be extended. So we can think of an extension like this as being positive, and we can think of a compression as being negative.
So it's not, so the x-axis is not extension, it's extension from one point. Or
Correct, from the equilibrium position, 100%. So let me
Oh.
go to the energy one. Then you can see when I plot the graph, can you see that the graph has a negative component?
Mhm.
So you can see that blue dot moving there, and it can move in the negative direction and it can move in the positive direction. But would you agree with me that the graph is symmetrical? In other words, it's rotated about the origin. So it's identical in the
Yes.
left-hand side than it is on the right-hand side.
Yes, sir.
Cool. And you're not going to get negative energy out of it because energy is always positive.
Mhm.
Yeah, so if you took the area under that graph, the area under that graph there is exactly the same as the area under the graph over there.
Okay,
So,
so
yeah. So not negative energy, negative extension or negative compression, and then positive extension and store. And the interesting thing is it's symmetrical. If you squeeze a spring by a centimeter and if you extend it by a centimeter, if it obeys Hooke's law, it stores exactly the same amount of energy. So if you look at the energy value here, with a +1 extension, it stores 50 joules. And with a -1 compression, it also stores 50 joules. Make sense?
yes, sir.
Cool.
Thank
And then the
you.
question is, so if I compress it and it wants to go back to its equilibrium position, in which direction is it going to move?
Right.
It's going to move right, correct? Because it wants to go back to equilibrium. So if it is there and I let it go, it's going to go over there. And then the opposite is true. If I pull it there, which way is it going to want to go?
Back to equilibrium.
Back to equilibrium. So it's going to go back to left. Because it's always going to restore itself back to equilibrium unless you overextend it, in which case you've broken the spring, and then it'll have a different spring constant and a whole bunch of different calculations involved. Cool, guys, it's the end of your lesson, so I don't know if you have another lesson, but I'm going to let you go just so that we get used to sticking to the time. So I'll upload the pictures and the graphs and everything to Google Classroom as well as the video.
Thank you, sir.
See you guys
Thank you, sir.
see you on Tuesday next week. Carry on working on momentum.
Okay, sir.
Cool, guys, bye.